Okay, so last time I explained these results of Kudla and Millson from the late 80s, where they construct these analogs of classical theta series, but whose coefficients are geometric objects, cycles on an orthogonal Shimura variety or cohomology classes on an orthogonal Shimura variety. So with this done, you kind of imagine for a moment that you're Steve Kudla, and you've got these beautiful geometric analogs of theta series, but you also have at your disposal a vast encyclopedic knowledge of everything related to theta functions and the theta correspondence and the Weil representation. And so you start to ask, which parts of this automorphic theory can you try to carry over into this new geometric setting? And he picks something very particular. He picks the Siegel-Weil formula, one of the foundational stones of the theory of theta functions, and says, can we geometrize this? So before I explain what this geometrization is supposed to be, I have to tell you what the classical Siegel-Weil formula is. So in the first lecture, we had a quadratic space, and we used it to construct Siegel modular forms. So there was an orthogonal group and a symplectic group, the symplectic orthogonal dual reductive pair. And in this lecture, I'm going to switch to the unitary dual reductive pair. And I can tell you now the main reason for this, which is that at some point in this lecture, I'm going to want to start seriously talking about integral models of Shimura varieties. And the integral model, there is a perfectly nice integral model of the orthogonal Shimura variety, but because the orthogonal Shimura variety is only of abelian type and not of PEL type, it doesn't have a nice moduli interpretation, which makes it hard to explain what the integral model is. But in the unitary case, it's much more concrete. So instead of quadratic spaces, today we're going to fix a quadratic imaginary field. And let's even fix an embedding into the complex numbers. Quadratic. And instead of a quadratic space, a Hermitian space. V, and the Hermitian form I'll denote with angle brackets over E. So at the moment, there's no restriction on this signature. It's just any non-degenerate Hermitian space, and n will be its dimension. Okay. Okay, and instead of the special orthogonal group, we're going to look at the unitary group, thought of as a reductive group over Q. And the role of the symplectic group in this lecture is going to be played by a quasi-split unitary group. So you just have to remember there's two unitary groups in play, and they have nothing to do with one another. I have one unitary group determined by this choice of Hermitian space. And for the other one, I'm just going to fix, for the moment, an arbitrary positive integer d. But eventually, I'm going to take d equals n. And consider the quasi-split unitary group H sub d, which is also called UDD, which so I want this concretely realized as 2D by 2D matrices. So it's inside the restriction of scalars from E down to Q, or GL 2D over E. And what is this? This is preserving, it's the group of isometries, preserving the standard skew Hermitian form on E2D defined by the skew Hermitian matrix, the identity minus the identity. Okay? Okay. So there's a Weil representation in this situation, just like in the orthogonal symplectic case. But I want to, now that we have this sort of representation theoretic way of thinking about theta functions introduced by Weil, we might as well just go all out. After Tate's thesis and Jacques Langland's, let's just work with automorphic forms on Adel groups. So there's a local Weil representation at every place. So there's a Weil representation. Omega. Well, let me just say that there is a Weil representation of the adelic points of this quasi-split unitary group on the adelic Schwartz space. Take our Hermitian space, tensor it with the Adels of Q's, take D copies of it, and look at the Schwartz space of that module over the Adels. Okay, just as I explained last time, it's not easy to define it, but so I'm not going to try. It exists, but whatever it is, our unitary group G acts on the underlying space, or its adelic points acts on the underlying space in an obvious way. And this Weil representation of the quasi-split unitary group commutes with the action of the unitary group of V. On the underlying space. Acting diagonally on the D copies. And so with these two commuting actions, so we get an action omega of the product. The adelic points of the quasi-split guy, the adelic points of G on the whole short space. And then the adelic analog of Weil's construction of theta functions is the following. If I take for any Schwartz function phi, define the theta kernel. So the theta kernel is going to be a function of two variables, depending on our Schwartz function. And it's defined in exactly the same way as I defined the theta function last time using the Archimedean Weil representation. You take a Schwartz function, phi, you take the h and the g, and together they act on that Schwartz function. You get a new Schwartz function, which you can then evaluate at any rational vector, and then you sum over all the rational vectors, d tuples of rational vectors. That's the theta kernel. So this is an automorphic form in two variables. So it's not obvious from the definition of the Weil representation, even if I had written it down. But in the variable h, it's left invariant under the rational points. This is a consequence of Poisson summation. And in the g variable, it is kind of obviously invariant, just because the things that I'm summing over are permuted by the rational points. Okay. So this is, one uses this to form theta lifts. You can, if you have an automorphic form on the group H, then you can integrate against it in the H variable to get an automorphic form in the variable G, and vice versa. So you can lift automorphic forms, or at least cusp forms, back and forth between the two groups. But that's not quite what we're going to do. So the Siegel-Weil formula so Siegel-Weil plus a lot of other people. In its core form, it was due to Siegel. It was improved by Weil. It was further improved by Kudla and Rallis. And Ichino. And it says the following, more or less. So for most d greater than or equal to 1, if you take this theta kernel in two variables and integrate out the g variable, to get an automorphic form on the quasi-split unitary group. This is not just any old automorphic form on the quasi-split unitary group. It's a special value of an Eisenstein series. So EH evaluated at n minus d over 2 phi, where EHS phi is an Eisenstein series. On the quasi-split unitary group. With a function, so the normalization here is that the functional equation is in S goes to minus S. And what does this word most mean? Well, the issue is that there are things that can go wrong here. So, for example, there are choices of d for which the theta integral diverges, and you have to worry about that. Depending on what d is, you may be inside or outside the range of convergence of the Eisenstein series. And if you're in the range of convergence of the Eisenstein series, there's no problem. If you're outside the range of convergence, you have to use meromorphic continuation. You might hit a pole, which is bad. And what's really confusing is that the choices of d for which the left hand fails to be defined and the right hand fails to be defined might not even match up. And so most is like, this is true for most. And in particular, it's true when d equals n. So the case that we really care about. But if you want to understand what happens when things go wrong, you have to look in these papers of Kudla and Rallis and Ichino on regularized Siegel-Weil formula. It gets pretty complicated.
Would you say with respect to which parabolic is
the Siegel parabolic. The question was which parabolic is it the Eisenstein series induced from? And it's the Siegel parabolic of block upper triangulars. Siegel, because it's unitary, but you know what I mean. Yeah, I mean, I'm never gonna tell you what the Eisenstein series is, which is unfortunate because it's actually really interesting. I mean, how does it know which Hermitian space V you're working with? This is an interesting question that I'm not going to get into. When I first started preparing these lectures, I considered doing all three on arithmetic Siegel-Weil, because you could easily do that, but it would get too into the technical weeds and less fun for me. And for you, but more importantly, less fun for me. So, okay. So I want to back up a bit just to explain what this has to do with the sort of classical theta series in the sense of Jacobi and Siegel that I wrote down last time, because I think it's kind of illuminating. So, example. let's assume that our Hermitian space is positive definite. And fix a lattice. Fix an OE lattice, L inside of V, on which the Hermitian form takes integral values. And once I fix a lattice, that actually gives me a very natural choice of Schwartz function here. So at the finite places, I can take the characteristic function of the lattice. So choose phi, my Schwartz function will be factorizable. So for the finite part, I'm just going to take the characteristic function of, I take my lattice, I take its profinite completion, I take d copies of it, and that's sitting inside of v hat d. And if you remember from the last lecture when we just had the Archimedean Weil representation, and I explained how to recover the classical Siegel theta series from Weil's construction, there was a natural choice of Schwartz function at the Archimedean place, just given by the standard Gaussian. And that still works here. So phi infinity of a tuple, so here x is x1 up to xd in V R d, and I just take e to the minus 2 pi, the Hermitian norm of x1, all the way down to e to the minus 2 pi, the Hermitian norm of xd, the product of the standard Gaussians on the two components. Great choice of Schwartz function. So then what happens? Okay, so now the real reason I'm doing this example is to kind of establish some notation, because in the first lecture, I expressed my Siegel modular forms as actual functions on the Siegel half space. So it was all very classical, and now we've switched to this idyllic language. So from this Schwartz function, in the quasi-split variable, I can de-atomize it into a classical object on the Hermitian analog of the Siegel half space, which is a classical Hermitian modular form, which is not a familiar thing to most people. And I'm not going to define what a classical Hermitian modular form is. I'm just going to indicate enough that you can hopefully get the idea. We can de-atomize the automorphic form H, G, phi to get a classical, quote unquote, Hermitian modular form on the Hermitian half space, which I'm going to denote script HD, the same notation I used for the Siegel half space, which is, I mean, if you want to know about these things, you look in the works of Shimura, because Shimura loves this classical language. He has very little interest in automorphic representations. He wants to think about functions on the space of all d by d complex matrices with the property that their imaginary part is positive definite, but the imaginary part doesn't mean the literal imaginary part of the matrix. The imaginary part, for some reason, means you take tau minus the transpose of tau conjugate and you divide that by I. That's a Hermitian matrix. And you want that to be positive definite. Tau such that is positive definite. That's the Hermitian half space. And this thing okay, has a natural action of the real points of our quasi-split unitary group, which if you write elements of the unitary group as block matrices, it's exactly the same action as in the Siegel case, and you can imagine what a modular form means in this context. Okay, so you take this theta function, you de-analyze it in the h variable, you get some function in this tau variable, but still also in the variable g. Okay, so call this de-analyzation theta tau g phi, but also suggestively call it, because the phi was completely determined by the lattice, I'm going to call this theta g L of tau. And Hermitian modular forms have Q expansions, just like Siegel modular forms. It has a Q expansion. Theta G L of tau is, and this is where things should start to look familiar, I'm going to sum over all Hermitian D by D matrices with entries in E. I'm going to count the number of D tuples of vectors in my lattice, but shifted by this element in the unitary group of the Hermitian space, take D tuples, and demand that the Hermitian pairing of X with itself is T times Q to the T, where the notation means essentially the same thing that it meant in the Siegel moduli case. So Q to the T means E to the 2 pi I times the trace of the matrix tau T. And for a tuple, a D tuple of vectors X, this means the matrix of Hermitian pairings of the entries of the matrix. The exact Hermitian analog of a Siegel theta series. Okay? And to go back to Siegel-Weil, what does this say? Now we're supposed to integrate over the G variable. So now we're gonna change the lattice. And because we're in a positive definite space, the integral is actually a finite sum. And the theta integral becomes, okay, so now I integrate this thing. Theta G L tau dg. It's a finite sum, and it's a finite sum over what? Well, you think about what lattices you get when you start with a fixed lattice and then shift it by elements in the unitary group. Every lattice that you get will be everywhere locally isomorphic to the lattice that you started with, but then you're modding out by the G of Q, so you identify two lattices when they're actually isometric. So it's a sum over L prime of this classical thing, L prime of tau, where L prime runs over all lattices in V isometric to L everywhere locally. But then you take them up to global isometry. In other words, the sum is over all lattices L prime in the same genus as L. And the Siegel-Weil theorem says it's actually an Eisenstein series. And the same is true in the orthogonal case. So this is the value of an Eisenstein series. And so last time when I started talking about the classical forms of Jacobi and Siegel, Jacobi derived these beautiful formulas for the number of ways to represent an integer as a sum of 4 squares or a sum of 8 squares. And when I was taught these proofs, the proof is you write down the theta series, whose coefficients are these representation numbers. You show that it's a modular form, and then by some miracle, the space of modular forms in which these things live are so small that there aren't any cusp forms. So the theta function has to be expressible in terms of Eisenstein series, whose coefficients you can compute, and you win. But it's not an accident at all. It has nothing. It's not really because there are no cusp forms. It's just because you always you don't get nice formulas when you just look at one theta series. But when you average over a genus, average. There's like you have to divide by the size of the isometry group of the lattice. It's an average. But when you average over all the lattices in the genus, you just always get a value of an Eisenstein series, and you always get beautiful formulas. Which is why Siegel was so interested in this. Okay, so that's the Siegel-Weil formula. So Kudla says, great, can we somehow incorporate this into this new theory of geometric theta series that he has with Millson? Okay, so let's switch and quickly talk about unitary Shimura varieties. Quickly, because I'm just going to basically write down a bunch of things and tell you that everything is exactly like in the orthogonal case. Question? Yeah, it is magical.
But why did you expect that it should be true? If you don't know this,
I mean, I don't know how to say that, except that because you're averaging over the genus, whatever the Fourier coefficients of this are, they should somehow only depend on everywhere local data, which means that it ought to be something computable. The reason why you get an Eisenstein series is harder. But the fact that the coefficients, just because you're averaging over the genus, it's kind of telling you that the coefficients are going to have product expansions. And the Eisenstein series coefficients also have product expansions, at least for the non-degenerate coefficients, the ones where t is non-singular. And so that suggests that, hey, maybe there must be some kind of local Siegel-Weil where you match up the local factors. But I'm deliberately not talking about that because that's kind of complicated and gets into like representation densities. The answer is it is magical. And beyond the fact that I've explained why it ought to be something nice, but why it's that nice thing, I don't have an explanation for. Okay. Okay, so now my Hermitian space is going to have signature n minus 1, comma 1. No longer positive definite, but not so far off. I'm going to think of V tensored with R as a C vector space because C is E tensored with R, or Hermitian space even. G is still going to be the unitary group of V. And the Hermitian symmetric domain that G of R is going to act on is going to be the negative definite C lines in VR. So this is inside of projective space of VR, where I'm thinking of VR as a complex vector space. So you just take all the lines on which the Hermitian form is negative definite. So this gives you a Shimura datum. The reflex field E, usually, unless V has, this is just being picky, unless V happens to have signature 1, 1, in which case the reflex field is Q, but it doesn't really matter. So now we're going to fix an OE lattice, L and V, and a compact open K in the adelic points of our unitary group, stabilizing it. And that gives us a Shimura variety. M over spec E, whose complex points are the usual thing. So just fix K. And everything I said in the last lecture about the construction of special cycles and there's a tautological line bundle, it works word for word the same. So I'm not going to write out all the definitions again. As in the last lecture, where'd it go? The tautological bundle on projective space restricts to a holomorphic line bundle on D, which then descends to the Shimura variety. So we've got an L in pic M, which I want to think of as the codimension 1 Chow group. And for any D less than or equal to N, and a D by D Hermitian matrix from D E, special cycles. Z of T of codimension, the rank of the matrix, and then exactly as in the last lecture, in the Chow group, we shift them by intersecting with the tautological bundle to get something of codimension D. So L inverse D minus rank of T times okay. And exactly as in the last lecture, you can assemble these into the coefficients of a generating series, which is then a Hermitian modular form. But that result turned out to be significantly harder than the proof in the orthogonal case, and it was only proved about a month ago by Raum. It took a while. There are technical issues. So, brand spanking new theorem of Raum, 2026, theta km of tau, which is now the sum over Herm d E C T Q to the T is the Q expansion of a Hermitian modular form valued in the Chow group. When you apply the cycle class map to cohomology and ask for modularity with coefficients in cohomology, this was covered by Kudla and Millson. It was already known in cohomology. The improvement to the Chow group is what Raum just did. where, I'm going to shamelessly go back and forth by Hermitian modular form, i.e. an automorphic form on our quasi-split unitary group. Okay.
Are the ideas more or less the same as in one of mathematics?
The structure, it's so new, I haven't read it yet. But yeah, the general idea is the same, but the technical details are significantly more complicated. There's the Brunier-Raum theorem was, I think, 2013. There's a 13-year gap, and it's not because nobody was trying. There's at least one example of a poor PhD student who thought he had proved it. Well, there were two PhD students who, one of them thought he had proved it, the other one said no, and here's the mistake because I tried to do this. So finally Raum just said, okay, I'll do it, but there's a reason it took so long. There's a genuine technical complication. Okay. That is the main issue, yeah. Right, last time I said that the theorem of Brunier-Raum was really the theorem of Brunier and Raum and Li-Zhang and Borchards. And the part that Li-Zhang did still works pretty much the same in the unitary case. It's the convergence issue that Brunier and Raum did that was hard to extend. But it was known when E is one of, I think, 4 quadratic imaginary fields, not just those of class number 1, but the ones for which the naive norm form is a Euclidean norm, stronger than class number 1. For those, it worked. Okay, right. So here's a theorem, which in the setting of orthogonal Shimura varieties is due to Kudla. And in the unitary case, it's due to Deng, a student of Chao Li. So this is geometric Siegel-Weil. So let's look at the special case where D is n minus 1. I never said this, but our Shimura variety, well, our Hermitian domain here has dimension n minus 1 as a complex manifold. So this is where we're looking at the dimension of M, and so we're getting a generating series of 0 cycles. Okay? So this theta km of tau takes values in 0 cycles. Tau n minus 1 of M. Then the theorem is that you can just take the degree, theta km of tau, which is the sum over t of the degrees of these 0 cycles. This is not the theorem, this is the definition. Is the value at s equals a half of an Eisenstein series. E tau s on the Hermitian half space of degree n minus 1. Now, okay, this comes with some caveats. Like, for example, this theorem is probably not true. It's true if the Shimura variety is compact, which almost never happens. It sometimes happens in signature 1-1, but when you go past that, it's not true. So this theorem is literally true in the extraordinarily rare cases where the Shimura variety is a curve. The real theorem is that you replace where am I? Here. Let's say. So warning, M is almost never compact. Which means that the degree map on 0 cycles doesn't really exist. It's a fiction. So this theorem really applies to compact versions of M over CM fields. You replace the quadratic imaginary field with a CM field over some totally real field. You cook up pretty much the exact analog of the Shimura variety, but when your totally real field is strictly greater than Q, it suddenly comes out compact. The theorem makes perfect sense and is true. But something like this in the non-compact case is something that's not yet known and probably looks a bit different. Whew, okay. Move the board. It's the Hermitian half space. Hermitian Eisenstein series. Okay, so that's great. But Kudla says, okay, but it's not the central value. I want the central value. So here we go. This is where the lecture really begins. All right. Section 3, integral models. All right. I'm going to keep the same V of signature n minus 1, 1. Keep the same Shimura variety, but now I'm going to make a stronger choice. So assume that our chosen lattice L and V is a self-dual lattice under the Hermitian form. That's a very strong restriction. For a fixed n, there are only finitely many choices of V that admit a self-dual lattice, but they exist. What we want now is a regular integral model. M of our Shimura variety. Okay. So here's how you do it. You run into a really confusing point right away, which is that given a Hermitian space for a quadratic imaginary field, there's actually more than one Shimura variety you can associate to it. And somehow I haven't exactly specified which one I mean. The one that I mean is almost but not quite the one that has a moduli interpretation. But it's very close. So here's how we're going to get an integral model. Okay. Let first script m 1, 0 over spec OE be the moduli space, moduli stack of elliptic curves E over S, where S is some OE scheme, with complex multiplication. So an action of OE. So that's weird notation for the moduli space of CM elliptic curves. The 1, 0 is because imagine E is over the complex numbers and it has complex multiplication, i.e., there's two ways to normalize the complex multiplication, because I can look at how OE acts on the Lie algebra of E, a one-dimensional C vector space, and it can either act through the embedding that I fixed at the very beginning of E into C, or it can act through the conjugate embedding. And the 1, 0 means I choose the natural embedding and not the conjugate one. So normalized
so that OE, if OE acts on E, then it acts on the OS module. So the Lie algebra of E, if E is over an arbitrary base scheme, is a line bundle on S. So I think of it as a rank 1 OS module, and the endomorphisms as an OS module of a rank 1 OS module is just OS. And I demand that this composition be the structure map here. Which is just a fancier way of saying the same thing I just said when E is over the complex numbers. And if I chose the conjugate of the structure map, I would have called it 0, 1. Okay. Okay, I need coffee for the next one. Ooh. It's cold, but any port in a storm, right? Okay, now, n minus 1, comma 1. Be the moduli space. Whose points, let's say whose S valued points, where S is some OE scheme, are, okay, I mean, they're going to be triples. Strictly speaking, this was a triple too, because I've got E, I've got the choice of action of OE, and the third element in the triple is the unique principal polarization of the elliptic curve, so I didn't write it. But here I need to write it. AI lambda, where A over S is an n-dimensional abelian scheme, I is an action of OE on that abelian scheme. And lambda from A to A check is a principal polarization. And there are some compatibilities between these things, which maybe I won't write out in full. The principal polarization induces a Rosati involution on the endomorphism algebra. And I demand that that Rosati involution restricts to complex conjugation on the image of OE. It's a compatibility between the OE action and the polarization. So let me just say, these are compatible in the sense I just said. But I want to explain what the sub n minus 1 comma 1 means. And such that the action, the induced action of OE on the Lie algebra of A, so this is a rank n vector bundle on S, satisfies a signature n minus 1 comma 1 condition, which is complicated when you really want something that's a regular integral model, and the complications come mostly in the at the primes dividing the discriminant of the quadratic imaginary field. So I'm just going to tell you what this condition is away from the bad primes. So if the discriminant of the quadratic imaginary field is invertible on our base scheme, then the condition is easy to explain. And the condition is just that the Lie algebra of A decomposes as a direct sum that I'm going to call the n minus 1 comma 0 part and the 0, 1 part, where this thing is a vector bundle of rank n minus 1, and OE acts through the structure map. And the other part is a line bundle. Rank 1 and OE acts the other way through the complex conjugate of this structure map. Acts the other way. So again, you should just imagine that you're over the complex numbers. My Lie algebra is just an n-dimensional vector space. OE acts on it. I want the OE will act through some elements of OE will act through some matrix, and I want that matrix to be diagonalizable. And there's n minus 1 entries where it's through the embedding of E into C, and then one last guy where it acts through the conjugate embedding. That's what this says. Okay, now a leap of faith. Fact. True fact. There is an open and closed subscheme. Script M, inside of, I take the product of these two moduli spaces. So some union of connected components whose generic fiber admits a finite étale map to our Shimura variety. So the Shimura variety that I've described, at least if you're willing to pass to a finite étale cover, it has a moduli interpretation as pairs of an elliptic curve and an abelian variety with a bunch of extra properties, but you have to exclude some pairs. It's pretty close to being a moduli space. Very close. Good enough for government work, as they say. It's a low bar these days. But so from now on, I'm just going to replace our Shimura variety by this finite étale cover and just pretend that this is an integral model of M. I mean, you can always take a quotient afterwards when you're done to get back to the original M. It's fine. Details. And so now, I mean, I omitted the definition of all of these cycles and the tautological bundle in the unitary case, saying it's the same as the orthogonal case. But the real reason that I omitted carefully writing them down is now I'm going to carefully write them down, but using the moduli interpretation. So now let's just work with this étale cover. Okay. Sorry? Sorry? Level structure. Yeah. Once we fix the self-dual lattice, just take the full stabilizer of that. And you get Deligne-Mumford stacks, but let's not worry about that. Okay. All right. Over M, we have a universal pair. I shouldn't have called, why did I call it E? I meant to call it A0 because that was terrible. Nobody complained that I'm using E in two ways. We can't do that. Really? Nobody noticed? What? Okay. My elliptic curve is called A0. So, yeesh, okay. I think that's good now. Okay. Yeah, we're good. Okay. So over this moduli space, we have a universal pair. There's some universal elliptic curve with complex multiplication and some universal abelian variety. Each of those has a Lie algebra, which is now some vector bundle on the base. And modulo this business about invertibility of the discriminant, the Lie algebra of A even has a distinguished rank 1 summand, which means that from A0 we get a line bundle, from A we get a line bundle. So let's tensor them together. Okay, we have a universal pair and a line bundle. Script L, which is, if you painfully work this all out, its dual is the Lie algebra of the universal elliptic curve, tensored with, you take the Lie algebra of the universal A, but you only take the 0, 1 part of it to get a line bundle. So that's what L is under the moduli interpretation. And now I have to explain what these special cycles are under the moduli interpretation. And this is the fun part. So this was worked out by Kudla and Rapoport. Okay, want moduli interpretation of the special cycle Z of t, we can intersect with this line bundle that we've got to get in the correct codimension. So, fix an OE scheme. S, if I give you a point, an S-valued point of our moduli space. Both our elliptic curve and our A have OE actions, so I can look at the space of OE linear maps between them. And Kudla and Rapoport made the marvelous observation that this Helm space is actually a Hermitian lattice. It has a Hermitian form on it. So define positive definite Hermitian form bracket xy on the OE linear maps from A0 to A as follows. Maybe I should switch. Where am I? Positive definite form by. Okay, here we go. I've got my elliptic curve. X there, X and Y are both elements in this Helm space. So X gives me a map to A. A is polarized. Y is a map from A0 to A. It has a dual. A0 is an elliptic curve. There's a unique principal polarization. So this is A0. X and Y together give me a map from A0 to itself. And everything is OE linear, which means this is an OE linear map from A0 to itself. But the OE linear endomorphisms of an elliptic curve with complex multiplication by OE, it is OE. There are no more OE linear endomorphisms apart from the complex multiplication. And so this is the definition of bracket xy, which is an element of OE, which is and OE A 0. That turns out to be a positive definite Hermitian form. The positivity comes down to the positivity of the Rosati involution in the end. Pretty wild, huh? Okay, so now I can tell you the moduli interpretation of Z of t. Sorry? For what? For? Oh no, I've defined I've defined these moduli spaces M1s. Is there a uniqueness statement? Well, yes. I'm not making a choice. I have specified a particular M inside of this product. I claim, well, there is a unique open and closed subscheme whose generic fiber is isomorphic and is a finite Attell cover. Well, maybe that's not a theorem. But it's unique in the sense that it is, at least if you stay away from primes dividing the discriminant, it is the canonical integral model in the sense of Milne and Kissen. It satisfies a canonicity property. So it's unique in that sense. But it's also unique in the sense that I've really picked out a thing by the long description that I've given. So I'm not really making a choice. Sure. Yeah.
I think you prefaced this section by saying Kudla wanted to get the central value for the Einstein.
Central derivative, but yeah, go on.
Yeah, so why did you do this setup? Why do you use the integral model?
You're asking me how Kudla thought of this idea. He knew his work with Millson, and he knew Siegel-Weil, and he also knew Gross-Zagier and some other work that Gross and Keating had done, and he somehow put it all together. It was an insight he had. No reasonable person would guess this. Only Steve. Yeah. Okay, definition. Special cycles.
So there's no nice letter accounting for
No. When Kudla and Rapoport came out with the first of their two papers describing this, I think they had already been working on it for 10 years. It was a long process. It's okay. Let's start. Yeah, okay. No, this is going to work out. Okay, let's start with special divisors. So let's just say I give you a little t in E, which I'm thinking of as a 1-by-1 Hermitian matrix, which means actually if it's a 1-by-1 Hermitian matrix, it actually better be in Q. Let's script Z of T. So this is going to be some moduli space that maps to our M. Be the moduli space of triples. Well, moduli space whose S points, where S is an OE scheme, are A0, A, and X. Of course, A0 is itself a triple, and A is itself a triple. So where the pair A0A is an S-valued point of M, which makes sense given that M lives inside of this product. And then what is this X? X is one of these things, an OE linear map from A0 to A whose Hermitian norm is T. And given the things that I said last time, you can probably guess what's next. If I instead take capital T to be a D by D Hermitian matrix, it's the same definition, except instead of one of these guys, you take a D tuple of these guys, and you demand that the matrix of Hermitian pairings is the Hermitian matrix capital T. So more generally, for T in Herm D E, define Z of T to M to be the modular space of A0, A, and X, where X is now a D tuple. Where this bracket XX means the same thing as way back when we had these Hermitian theta series. Sorry? The form, this is a projective, finitely, it's a finite projective OE module. And so it's OE linear, and the Hermitian form is OE linear in the first variable and conjugate OE linear in the second variable, and OS plays no role in it. It's an OE module. It's not a sheaf or a vector bundle or anything. It's literally an OE module. Okay. And of course, now set script C of T to be Z of T intersected with this line bundle on the integral model the correct number of times. Obviously, except okay, there's a problem, which is that it is true that if you take this object, this scheme, and pass to the generic fiber, you really do recover the things that we already had in the generic fiber. But if you want to insist on a moduli interpretation like this, you're forced to accept the following uncomfortable fact, that this thing is almost never equidimensional. This doesn't really make sense. This thing in the generic fiber has codimension the rank of T. But in finite characteristics, it typically has irreducible components of the wrong dimensions. And that's somehow because the problem comes if you're at like an FP bar point where both A0 and A are supersingular. There's just somehow, it's too easy to have maps between them. Like when you're on the supersingular locus, you basically, you always can find a D tuple that satisfies this property, which means that no matter what D is, this cycle tends to contain the entire supersingular locus of this Shimura variety, which has roughly half the dimension. So you're kind of always stuck with the supersingular locus. So you have to somehow find a way to make sense of this. And the way to make sense, by far the most efficient way to make sense of it is to just mumble the words derived algebraic geometry. And then everyone, since nobody really understands this, everybody just says, yeah, sure, why not? So, I mean, it comes up already. I mentioned last time, but never wrote, that in the orthogonal case, Kirti Metapusi and I had a version of these modular generating series on the integral model of the orthogonal Shimura variety. And the same problem already comes up there. And one way or another, you have to do some kind of derived thing to make sense of this, to correct the codimensions. And in the orthogonal case, Kirti and I did like something very ad hoc that also works in this unitary case. But then Kirti went back and did it right and has a preprint where he uses like the full force of derived algebraic geometry to go back, redefine these moduli spaces as, he writes down functors on derived schemes and proves that these are representable by derived schemes, and then uses these derived schemes to construct actual cycle classes. So this has that great big caveat that there's a lot of derived stuff implicit in here one way or the other. But I'm going to ignore all of that. And move on. Okay, because here's the theorem. At last, section 4, arithmetic Siegel-Weil. So now we're going to look at d equals n, where this integral model is a scheme of dimension n. So when we take d equals n, now we're looking at the Chow group of 0 cycles. And you can talk about their degrees, kind of. So theorem. So the first work on this, all the definitions and the idea, and the first results in this direction are due to Kudla and Rapoport. And then much, much more was done by Chao Li and Li-Zhang. And then more, so I'll write the theorem and then tell you who did what. And then there's he, Li, Shi, and Yang. And here's the statement. There is an Eisenstein series, a Hermitian Eisenstein series, E tau S, on the Hermitian half space of degree n. So I'm taking d equals n. So in other words, an Eisenstein series on this quasi-split unitary group H sub n that I defined at the beginning. With a Q expansion. So E tau S is the sum over n by n Hermitian matrices of some coefficients that I'll call E t of S, Q to the t. Vanishing at s equals 0. In particular, this Eisenstein series is like, but not literally one of, the Eisenstein series that appeared in the original Siegel-Weil formula. Those did not vanish at s equals 0. with the following property. For all positive definite T in Herm and E, the zero cycle. So in the positive definite case, our zero cycle C of T, we don't have to hit it with this line bundle. It really is just the Z of T, except that this thing may not actually be zero dimensional. So you have to understand it in some derived sense. The zero cycle has degree Z of T equals the derivative. Well, let me just write E T prime at 0. It is the central derivative of the tth coefficient of the Eisenstein series. That is the arithmetic Siegel-Weil formula. I went 5 minutes over last time. I will not do that this time. Let me just say, I'm tired. I don't want. I just didn't want to say I don't want. But let me say a few things about this. Right. So first of all, Kudla and Rapoport worked out precisely those matrices T for which this zero cycle is literally a zero cycle. And then this degree, I mean, it's some non-reduced zero-dimensional moduli space, and this degree means you just count how many points are on it, but you count them with multiplicities equal to the lengths of the local rings. And they figured out when it actually is zero-dimensional, added up the lengths of the local rings, and proved this. Li and Zhang did it, so it turns out, under this assumption that T is positive definite, whatever this Z of T is, even if it's not literally zero-dimensional, if it's non-empty, it's supported in a single non-zero characteristic. Very kind of localized thing. And they made sense of this degree and computed it in all cases where that single non-zero characteristic is not a divisor of the discriminant of the quadratic imaginary field. They did all the unramified cases. In particular, they made sense of the degree even when this is not actually zero-dimensional. And then he, Li, Shi, and Yang did the ramified primes. So it's known in full generality. And there's further work. I mean, there was this assumption at the very beginning that we chose a lattice that was self-dual under the Hermitian form, which is responsible for the condition that the A in the moduli problem have a principal polarization and not some other polarization. So there's some work in the non-principal case. But, and finally, and hopefully I'll have time to say something about this in the next lecture, it feels like you've somehow done something important. But what have you done exactly? I mean, you've connected the geometry of this Shimura variety to something in the world of automorphic forms. So what are you going to do with it? Well, if I had another 15 minutes, I would tell you about the arithmetic Rallis inner product formula. So this Eisenstein series appears in a kind of Rankin-Selberg style integral, the doubling integral. And starting from this, Yifeng Liu and Chao Li proved the arithmetic Rallis inner product formula, which is a kind of Gross-Zagier formula that relates intersections of these special cycles to the actual central derivative of a Langland's L function by exploiting the fact that this Eisenstein series is the one that appears in the doubling integral. And there's a p-adic version of this due to Daniel Desenyi and Yifeng. So you can ask him about that instead of me if you want to know more. Although hopefully I'll say something about that in my third lecture, because in my third lecture, I'm going to take this and replace the unitary Shimura varieties by moduli spaces of Hermitian shtukas, a curve over a function field, and try to explain an analog of this in the function field setting, and then hopefully get to a result in the function field setting relating intersections of cycles to higher derivatives of L functions. So that's the preview of coming attractions. I'll stop there. Thank you.